Algebra 2, Section 3.4, Use Inverse Operations. The inverse of a relation is a set of ordered pairs obtained by switching the coordinates of each ordered pair. So for example, here is our original relation where we have 5 different ordered pairs or 5 different points. The inverse of relation is just obtained by switching each x and y value. So the point 3, -1 would become -1, 3. The point 0, 2, well again, we'll switch the x and the y, making it 2, 0. And -1, -4 would switch to -4, -1. Be careful with this next one, 2, 2. Make sure you switch those. That's going to be 2, 2. I can tell if you don't. And the last point, -3, 5, would become 5, -3. So if we have individual points, it's very easy to find the inverse relation. Now let's look at what this would look like graphically. What we're going to do is we're going to graph each original relation point with dots. So each of these will be a dot on a graph. And the inverse relation we're going to graph with x's so we can tell them apart. And then we want to look and see if we can determine the relationship between the two graphs. All right, so get your graph ready. And again, the original relation points we're going to graph with dots. So I'll start with 3, -1, put a dot there, 0, 2, dot there, -1, -4, oops, put a dot there, 2, 2, dot there, and then -3, 5, and a dot there. All right, now for the x's for the inverse relation. All right, so -1, 3, put an x here, 2, 0, x here, -4, -1, 2, 2, so I'm going to have an x on top of the dot, and 5, -3. All right, now, comparing each point, we can see that this 3, -1 here flipped to -1, 3 here, and this point up here came down here, this point here came down here, that point stayed on where it was, and this point moved up here. So do you see any connection with there? Think about a line of reflection. Where would you draw that line of reflection where each point in the original would be reflected onto the inverse relation? Well, maybe you noticed it'd be the diagonal line where y equals x. Oops, let's see. So if we put this line through here, would be y equals x. Y-intercept 0 goes through 0, 0, slope of 1, up 1 over 1, up 1 over 1, up 1 over 1. And every point on that line, the x value equals the y value, right? We have points at 1, 1, 2, 2, 3, 3, 4, 4. And imagine that being a line of reflection. And you can see that each dot would be paired with an x on the other side of that line of reflection, which then also makes sense why this point stays on the line of reflection. And this will be true for any inverse relation, is that it will always be a reflection over y equals x from the original relation. We can find inverses from points. We can also find inverses of equations. So we're going to find an equation for the inverse of the relationship between y and x, and y equals -3x plus 5. Well, just like with the points where we switched each x and y coordinate, that's where we want to start with this, is we want to switch x and y. Now, everything else will stay where it is. -3 will stay where it is, 5 will stay where it is. It's just the x and the y that will switch. So that gives us x equals -3 times y plus 5. Then I want to go ahead and solve for y so that the inverse is also in y equals form. So let's subtract 5 from both sides. divide both sides by -3. And I'll write this in y equals form. So y equals -1/3 x plus 5/3. Go ahead and write that in slope-intercept form. Because next we're going to graph both the original equation and its inverse and compare the two. Okay, I'm going to graph the original equation with black and the inverse in red so we can see the difference. The original equation starts with a y-intercept of 5, so I'm going to go up to 5, put a point. The slope is -3, so down 3, right 1, because it's negative, so down is negative, so then to the right to keep it negative, down 3, right 1, down 3, right 1. And then I can go ahead and draw a line connecting those points. Now for the inverse, it has a y-intercept of 5/3, so I want to go up to 1 2/3, about right in there. Then slope of -1/3, so down 1 over 3, down 1 over 3. All right, then I'll connect those points, draw the line. Now we can see, just as with the points that we looked at earlier, these lines would be a reflection of each other over the line y equals x. You can see a mirror image where this point here matches up with the point over here, this point down here matches up with the point up here. And we could also do that by flipping around individual values. I have a point on the black line at 2, -1. So on the red line, I should have a point at -1, 2. And if I look, there it is, -1, 2. So one way to graph inverses, if I don't know the function, is just to select individual points from the original function and flip them to graph the inverse. Now let's find the inverse of this function f of x equals 1/2 x minus 3. And then we're going to look at if the inverse would be considered a function or not. Because even if a function has an inverse, the inverse may or may not be a function. All right, the original function, we have f of x equals 1/2 x minus 3. Then I can replace f of x with y, because f of x is just another way of writing the output or the y values. Then, just like in the previous example, I want to switch x and y, leave everything else where it is originally. And then I want to solve it for y, so I'll add 3 to both sides. So I get x plus 3 equals 1/2 y. Then I need to multiply both sides by 2. And make sure you multiply the entire side by 2. So I'll need to distribute that to 2x plus 6 equals y. So I have that y equals 2x plus 6. Now, if this is a function, I can write it in function notation for the inverse, which would be f to the negative first of x, which the negative first here is not a power. It just represents as the inverse of function f. But let's talk about functions first. For something to be a function, for each input value that I plug in, it will correspond with exactly one output. So as I plug in various values of x, I will get various values of y. Another way of thinking about this is if something is a function, it will pass the vertical line test, meaning if I graph it, the vertical line will only cross the function once. And anytime I have a diagonal line, like I would for my original function here, or for the inverse, I'd have, let's see, y-intercept of 6, slope of 2, so it looks something like that. Each x value, as I look along here, would correspond with exactly one y value. So the inverse here would be a function, which means I could write it in function notation. I'm using f to the negative 1 to show us the inverse of the original function f. And there we have it. Now let's look at g of x. Here is x squared minus 3. And we want to find its inverse. and then graph both the function and its inverse, and then determine if the inverse is a function of x. All right, so g of x, I'll first replace that with y. Then I'm going to switch the x and the y. So this will be x equals y squared minus 3. And now I want to solve for y. So add 3 to both sides. Then to get rid of the squared, I need to take the square root of both sides. And I have to remember when I take the square root, I have to put back in the positive or the negative because squaring something gets rid of the negative. When I'm undoing the equation or using inverse operations, I have to put the negative back in. So I have y equals positive negative square root of x plus 3. Now let's think about if this would be a function or not, if I can use function notation. Well, think about if I plugged in 1 for x. 1 plus 3 is 4, and the square root of 4 is 2, but then y would either equal positive 2 or negative 2. So for one x value, I have 2 y values. That means it's not a function, because for it to be a function for each x value, it has to correspond with exactly one y value. Well, let's see what this would look like graphically. All right, think about what g of x would look like. Anytime we have an x squared or quadratic equation, it's going to graph as a parabola. Now, if I start with a basic x squared and then subtract 3, that's shifting it down 3 from 0 to 0. So I'm going to shift it down 3. Or I could think about if I plug in 0, 0 squared minus 3 is negative 3, so I have a point at 0, negative 3. Then I can either follow the pattern of a basic parabola of going over 1, up 1 in both directions, over 1, up 1, over 1, up 3, over 1, up 3, and I can keep going over 1, up 5, over 1, up 5, or I could just set up a table of values and plug in points. Now, with parabolas, a good place to start is the vertex. If I don't recognize the vertex is at 0, negative 3, I could also find that by doing the opposite b over 2a that we looked at in a previous chapter. Now, if I look at, let's compare, if I plug in 1 for x, 1 squared is 1, minus 3 is negative 2, so that matches here. Negative 1 squared is 1, minus 3 is negative 2, so I can plug in points to match up with what I have graphed here. Then let's go ahead and connect those points with a smooth curve for a parabola. All right, and that would continue in both directions. Now, to graph the inverse, it might be fastest just to flip each point around. So I could look at this point at 0, negative 3 would flip to negative 3, 0. The point at 1, negative 2 would go to negative 2, 1. The point at negative 1, negative 2 would flip to negative 2, negative 1. So you can see our parabola is going to be sideways here. Let's do a few more points. 2, 1 would flip to 1, 2. Whoops, not there, right over there. And negative 2, 1 would flip to 1, negative 2 down here. And we can see, just connect those points, we get our parabola sideways. And once again, you can look at, think of the y equals x line being the line of reflection, and you can see how that lines up. Now, I mentioned earlier the vertical line test and said if a function passes the vertical line test, if a equation or a graph passes the vertical line test, it is a function. So look at the original black line. This parabola, anytime I draw a vertical line, it's only going to touch the vertical line in one spot. So it's a function. My original graph, the parabola, is a function. Now for the sideways parabola, as I come along with a vertical line, you can see it gets to the point where there are 2 places where it would cross that vertical line. Or for each input, there's more than one output for that x value. So this inverse here is not a function. So I really probably wouldn't want to use function notation like I did here to show it's an inverse function. I'd probably just want to say y equals. So it's still an inverse, it's just not a function. One more note on this problem is that if I wanted to graph this and I did not know the original function, I could just plug in values and I would see that, well, x has to be greater than or equal to -3 because I can't take the square root of a negative value. And if I had like -4 under the square root, I'd have -4 plus 3 is -1, and I get an imaginary number. So I would start with values at -3, plug in -3, I get the square root of 0, which is just 0. Then I'd plug in -2. -2 plus 3 is 1, square root of 1 is 1, and we get points at +1 and -1. And we can continue graphing that sideways parabola in that fashion. You learned about compositions in the previous section, and now we can see how we can use compositions to verify that two functions are inverses of each other. So if the functions, two functions, f and g, are inverses of each other, then both f of g of x needs to equal x and g of f of x equals x. So they undo each other and equal x, which should make sense since they are reflections over the line y equals x. So we're going to determine whether these pairs of functions are inverses of each other or not, and we're going to use compositions to do so. Now, I could, if I wasn't using compositions, I could just start with f of x, switch the x and the y, solve for y, and see if I get g of x. But I will want you to be able to use and recognize how to use compositions as well. So let's first test f of g of x for our first function. So we'll start out, inner function is 1/2 x minus 2. And then f of x says to take 2 times that input and then add 4. So the input now is the 1/2 x minus 2. Let's simplify here. Distribute the 2. We get 2 times 1/2, which would be x, minus 2 times 2, so minus 4, plus 4, and it does equal x. So far, so good. F of g of x equals x. Now, I need to also test g of f of x and show that it equals x as well. So starting with the f of x, 2x plus 4, and we're going to plug it into the g function, which says take 1/2 of the input and subtract 2. The input here is 2x plus 4. Distribute the 2, we get x plus 1/2 of 4, which is 2, minus 2 equals x. So yes, those are inverses of each other. Let's try the next one here. Start out with f of g of x. And let's plug in the g of x. We'll plug that into f of x. So we're going to take 1/3 of the input plus 2. And the input here being 3x minus 2. Distribute the 1/3. And that gives me x minus 2/3 plus 2, which does not equal x. So these are not inverses of each other. Now, a lot of times when we think inverses, we think just, oh, we'll just flip them around. Well, look at and compare these two. 2x plus 4 and 1/2 x minus 2. We can see in looking at those, there's some connections, there's some similarities, but no direct way to tell that they're inverses. And if you look at these, we had 1/3 x plus 2 and 3x minus 2. Again, we see some connections between the numbers, but without either using compositions or finding the inverse of one of the functions, we really can't just glance at them and tell if they're inverses or not. And let's look at one final example. Have you ever been a part of a bowling league? Well, let's suppose you belong to a bowling league in which each bowler's handicap, H, is determined by his or her average, A, according to the following formula. And a lot of times handicaps are applied to kind of level the playing field if you're in a bowling league. So h here, your handicap, is 0.8 times 200 minus a, where once again a is your average bowling score. If your bowler's average is over 200, then your handicap is just 0. They won't go into negative handicaps. So we want to rewrite this formula so that the handicap is the input and the average is the output. Now, another way of saying this is find the inverse of the function. But if we're to find the inverse of a function where our variables mean something, like here h being the handicap, a being the average, we don't want to switch the location of h and a. That changes the whole meaning of the whole problem. So again, in a real life situation, if you're finding the inverse, basically you're just solving for the other variable. So in this case, we want to get a by itself. Well, I could start by either distributing the 0.8 to the 200 in the a, or I could start by dividing by the 0.8. Now, and actually, I'm going to think of 0.8 is 8/10, which would be 4/5. So I'm actually going to think of it as 4/5 times 200 minus a. So instead of dividing by 0.8 and having a decimal within a fraction, instead I'm going to multiply both sides by 5/4. So then 4/5 times 5/4, that just equals 1, so those cancel. And now I have 5/4 times h equals 200 minus a. Then I can subtract 200 from both sides. Again, my goal is to get a by itself. So at this point, I would have negative a equals 5/4 h minus 200. Need to then divide both sides by -1. So a would equal negative 5/4 h plus 200. Or I might want to write that as 200 minus 5/4 h. So the inverse of my original function, where I have h equals, is now the equation a equals. But a still represents the average, h still represents the handicap. So to answer the next part of our question, if your handicap is 32, what is your average? Well, I could plug the 32 in for here, but then I have to rearrange the equation all over again to get a by itself. So it's probably much easier to go ahead and use the equation I just found and plug in h there. Go ahead and plug in h, see what you get for your average. Did you get 160? Well, that's much better than my average. I like to get over 100. That's always my goal. All right, well, that concludes lesson 3.4, using inverse functions. Thank you.